All right, here we're looking at the composition test, and the composition test for inverses is essentially a way of determining whether or not we're dealing with inverses or not. Because what happens is if I do the inverse and a function, and I take the composition of the inverse in the function, it's going to give me x. And it's going to give me just an x no matter which way I do this composition. So if I take the inverse and plug it into the function, which is what this first composition is telling me, it should equal an x. And then if I take the function and plug it into the inverse, which is what this second composition is telling me, it should just give me an x, all right? And so that's true if I'm dealing with inverses. And so the way we use this is basically if we have two functions and we're not sure if they're inverses, we do the composition test. We plug one function into the other function, and we do the composition one way, and then we do the composition in reverse, where we plug the second function into the first function, and we just see if we get an x each time. Because if we get an x each time, it means that we're dealing with inverses. Because if the functions are inverses, when I do the composition, it'll equal x. All right. For example, when I look at this first one, again, I just have to do the composition each way. And that's the real key to this thing, is that we have to do the composition twice, because we will get false positives every once in a while, where we'll get something that's an x, but it shouldn't, but it's still not quite an inverse function because we're missing some kind of restriction somewhere, okay? So for this one, if I want to know if these are inverses or not, I want to know if f and g are inverse functions of one another, I'm just going to do the composition test. I do f of g of x, and then I also have to do g of f of x. So you have to do the composition in both ways, all right? You have to do the two different compositions that are possible with the two functions. And now I'm just going to simplify each of these. I'm just going to start plugging in. So here I have f of g of x. Well, g of x is the 1/2 x plus 3/2. So I substitute that in for g of x. And I'm going to substitute that into the f function. So I have 2 times x minus 3. But instead of x, I want to plug in the 1/2 x plus 3/2. Because that's how the composition works. And now I just have to simplify. So here I distribute. That's going to give me an x plus 3. The minus 3 kind of tags along for the ride. I combine like terms, and I end up with an x. All right. So far it looks like these are going to be inverses, but again, I have to do the other composition and make sure that that is an x as well. All right. So I'm going to do the other composition. So I plug the 2x minus 3 in for f of x. I substitute that in. And now I have 1/2 x plus 3/2, but instead of x, I'm going to plug in the 2x minus 3. I go ahead and distribute. That's going to give me an x minus 3/2. And now I combine like terms, and I end up with just an x. All right. And so when I look at these, I now know that these are inverses because when I did the composition each way, I got an x. And the only thing that gives me just an x when I do the composition are inverse functions. Okay. So the answer here is yes. And keep in mind that we could find this another way. I could just find each inverse. Like I could take this function and switch the x and the y and see what I get. And if I found the inverse of this, I would end up finding that the inverse is a 1/2 x plus 3/2. All right, which matches my g function. But then I would also have to find the inverse of the g of x function. I would switch the x and the y, solve for y, and I'd find out the inverse of this guy is actually a 2x minus 3. So that's the other thing we can do. I can just find the inverse of each and then look to see if they match one another. And then I would know they were inverses as well, okay? In this particular example, the composition test is probably a little bit simpler and a little bit quicker, just substituting one into the other and seeing if you get an x out, okay? The math involved is probably a little simpler, okay? If I look at another one, if I look at something like this guy, again, I'm going to try the composition test here. So if I do the composition test, I'm going to do f of g of x. And then I'm also going to do g of f of x. So I have to do it each way. Over here I have f of, the g of x is the plus or minus square root of x minus 2. And I'm going to plug that into the f function. So this was x squared plus 4 times x plus 4. But instead of x, I'm going to plug in the plus or minus square root of x minus 2. And now I have to simplify, and the thing that makes this one really tough to simplify is the fact that I have that plus or minus. It means I have two things in there. How do I square something when there's actually two things in there? What I have to actually do is I have to simplify this twice, really, when it's all said and done. I have to do the positive version, which looks like this. And I also am going to have to do the negative version. It means two things, which means I have to do it twice. So I'm going to do the negative version as well. And really, if the composition test is going to work, each of these should give me just an x if they're inverse functions. See, so I have to do the positive version and the negative version. Over here, when I do this guy squared, remember I have to multiply that by itself, so I have to FOIL. And when I do, I end up with an x minus 4 root x plus 4. Here I distribute the 4, and I get a plus 4 root x minus 8, and then that plus 4 tags along for the ride. So now I combine all these like terms, and when I do that, I'm left with just an x. Here I do the same thing. I have to FOIL this first piece, so that's going to give me an x plus 4 root x plus 4. Here I distribute, and I get a negative 4 root x minus 8 plus 4. And now when I look at this, I combine like terms, and when I do, I'm left with just an x. So the overall value here when I do f of g of x is x, no matter which way I slice it. And so now with the second piece, I have to do the composition test again. So I do g of f of x this time being the x squared plus 4x plus 4. And really the trick with this one is the fact that when I go to plug this in here, that's going to be plus or minus the square root of what's in the parentheses. That x squared plus 4x plus 4 that I'm going to be plugging in right here, that can actually be factored into an x plus 2 squared. And that's the key to this one, the little trick that we have to recognize that perfect square trinomial. And now what happens, when I take the square root of this thing, it's going to give me plus or minus. Well, this is actually going to give me the absolute value of the x plus 2, which is like a plus or minus x plus 2. So what I end up with is plus or minus x plus 2. Well, a plus or minus times a plus or minus ends up just giving me the positive version, which is the x plus 2. And now when I do this, the x plus 2 minus 2, I combine like terms, just leaves me with an x. All right. So with the first composition, I got an x. With the second composition, I got just an x. So the answer is yes, these are inverses. And when you look at the amount of work that's involved here, and you look at all the little tricks that had to be done and the headaches that the plus or minus caused you, this is an example where just finding the inverse of each would be far easier than what we've actually done here. Okay, the process of doing the composition test here is not really the smartest way to do this problem. You'd be much better off finding the inverse of f of x and seeing if it matches the g of x, and then finding the inverse of g of x and seeing if it matches the f of x. Okay, but no matter which test we do, you have to do each. You have to do the composition both ways. You have to do both inverses in order to truly determine this thing. Okay, and if we look at this last example, here's why. All right, when I do something like this, let's do our composition test. So I want to do f of g of x, and then I'm also going to do g of f of x. So here h of x. Sorry, we're dealing with h this time. Let me try that again. There we go. So here h of x is the square root of x minus 2. So I do my composition test. That was x squared plus 2, but instead of x, I'm going to plug in the square root of x minus 2. The root and the exponent cancel each other out. It leaves me with an x minus 2. And when I add those together, it gives me just an x. All right? So it looks like we're going to have inverses here because it seems like things are working out the way they're supposed to. But then when I look at this second piece, I do h of f of x, which is the x squared plus 2. Well, here this would be x minus 2, but instead of x, I'm going to plug in the x squared plus 2. And so what happens underneath here is I combine like terms, and I'm just left with an x squared. But now the square root of x squared is technically the absolute value of x, which kind of translates eventually into essentially a plus or minus x, the positive or negative version of x when it's all said and done. So what happens is when I do the composition one way, I get an x. When I do it the other way, I get the absolute value of x, which essentially gives me two different x values, or two possible different x values, a positive version and a negative version of that x value. So these are not inverses because I didn't get just an x each time. The second time I got a positive or a negative x, and so these are not inverses. So the answer here is no, these are not inverses. And even if we did this the other way, what's going to happen is here when I do the inverse, when I find the inverse of h of x, it's going to end up giving me an x squared plus 2. It's going to look like it's right, but that x squared plus 2 is slightly off because it needs a restriction. And so it doesn't quite actually match the f of x, but we can't really see that algebraically. When I do the inverse of this guy, what's going to end up happening is I'm going to find the inverse of this one is actually plus or minus the square root of x minus 2. And so that's where the real discrepancy comes in. We can see that doesn't match our h of x, so the answer is no. But again, the point of that is that we have to do each inverse if we're going to do it that way. All right, just like with the composition test, we have to do each composition to determine that, okay? Unless I do one that doesn't give me an x first. As soon as I get a composition that doesn't equal x, if I had done this second composition over here first and saw that it wasn't an x, I can stop right there and say, no, these are not inverses because I didn't get just an x, okay? And so when we're doing our composition test, you got to do the composition each way. All right, and it's got to give you just an x each time, or they're not inverses. All right, the other option is to find the inverse of each, but again, you have to find each inverse and then compare it to the other function. Okay.